is Jason Molgaard. I'm from ARM, and we've seen a lot of examples this morning. Is that better? Yeah, just bend. How's that? Okay, so we've seen some great examples of actual products that are out in the marketplace today, and certainly that's interesting. I'm going to kind of take a step back and look at it more from a overall generic architectural standpoint. All right, so quick agenda. So do an overview of computational storage. I think a lot of people are pretty familiar with that, but I think it's good to set a baseline. Taking a look at fixed and programmable computational storage drive hardware, some data flow comparison, communicating with the CSD, interfacing, and then kind of switching gears to programmable CSD software, and then touch on current status. All right, so what is computational storage? All right, well, this is obviously currently being defined, and if you're not involved, then hopefully you can help control that. Since it is a standard, there's lots of verbiage to go along with that over on the left-hand side. I'm not going to read that, but you can kind of distill it down to what I have on the right-hand side. Compute coupled to storage to offload the host or reduce data movement. So the key is that we're trying to reduce data movement, we're trying to offload the host, and certainly that is, those are useful tasks. We've seen that in, from some of the folks who presented earlier. All right, so what is not computational storage? So I have a SmartNIC listed here as an item. I keep getting this question often in some of my conversations. So the reason I say that a SmartNIC is not computational storage is because it's coupled to the network, not to the storage. Okay. All right. So and then I think that so obviously that kind of violates the definition that I had provided about reducing data movement and offloading. But it also there's no latency reduction with a SmartNIC. And I'll get into a little bit more detail on that. And specifically what I'm referring to is if you did have an NVMe drive, for example, connected to a SmartNIC, you still have to package all the data up into NVMe protocol and move it over to that SmartNIC device, and you don't get the benefits of computational storage. So I will get into more detail on that as we go along. All right, so a few additional definitions from the technical working group. So of course, we've already kind of touched on fixed purpose computational storage. This is obviously a fixed function, but it can be configured. So it's, there is some flexibility there. We've got programmable. So it's a computational storage that can be programmed, and definitely going to focus on that. Then there's a kind of a generic term, a computational storage device, which is any one of three computational storage drive. So that's obviously the drive that we're familiar with today, U.2, M.2, whatever the case may be. It has storage on it. The computational storage processor that Stephen just presented from Dataflow, and then a computational storage array. I'm not going to really talk about computational storage processors or arrays today. So one of the hot topics that was in the BOF last night is, why do we need computational storage? Well, so the answer is that the volume of data that we generate is growing, expected to grow at 27% per year. That's a lot. And couple that with the fact that drive capacities continue to increase. So 16 terabyte SSDs available today, and HDDs. 32 is also available. That's a lot of data on the drive. And we don't want to move all of that data if we're looking for something very specific in that large volume. So we need to find new ways to manage that data. So how does computational storage help? Well, so for starters, the compute happens on the drive. So there's no moving of data. So that's definitely one of the key items. We also have lower latency. So, and the reason we have that lower latency is we don't have to package the data up in Fabric protocol and move it across an interface. So because we're not packaging that data and moving it across the interface, we save on bandwidth and power. So we just reduced our power. And one of the presentations this morning from Scott talked about the fact that he's able to allocate more compute on his drive because he's saving the power from moving the data across that interface. And I think this is the exact key benefit that we want to highlight. Only the results have to be delivered to the host when we have computational storage. We can have data-centric processing. If we know what the data is on the drive, the type of data, then we can download a workload that's specific to that. We don't have to have generic compute for whatever purpose. We can have it very tailored to that data. And then, of course, security, certainly not last, is last, but certainly not least. We don't have unencrypted data leaving the drive, so that helps, although obviously we've got a lot of other security measures in place that we need to keep in mind. So the diagram on the right here on this slide is kind of a simplified model. We've got a server making a request. The compute is circling away there, trying to come up with the answer, and then finally returns a result. All right, so I want to kind of set the framework here with a generic SSD controller hardware block diagram. So this is kind of a basic SSD structure that you might have in an ordinary SSD today. You've got a host interface over there, all the way on the left-hand side. You've got some on-chip or you've got some DDR that's on the device, a front-end processor or multiple processors managing your flash translation layer. And it is an embedded device, so you've got to have some peripherals, of course, so that you can debug it and figure out what's going on. And then, of course, you've got your data path that includes encryption, RAID, LDPC, that kind of thing, leading out to a multitude of flash channels. And each of those flash channels, of course, is connected to some multitude of NAND devices. So I've already mentioned a couple of areas where we do have compute already on the controller for this SSD. The front-end processor being one of them. You may or may not be able to just leverage that compute that's already there to do some additional compute on the data on that drive. But the bottom line is that for a computational storage drive, this kind of structure is still going to be in place. We still have to have the ability to move data in and out. It is a drive at the end of the day. All right, so if we take that same block diagram and we say, well, how would it change with fixed purpose computational storage? So the diagram shows a lighter blue box that's been added in. It's basically our compute function, whatever that fixed purpose may be. The rest of the structure is the same. So essentially what we need is a new pathway to that fixed function. Any function is possible, as we know. But it's fixed at reset. That's kind of obviously the definition. Or it may be, may require a reset if we want to change it. Let's say it's implemented in an FPGA and you want to download a new bit file. You have to do some kind of a reset or restart in order to get that new function started. But of course, it can be configured. It's not, you're not completely stuck. It's not, you've got some flexibility in terms of configuration and making sure that you've got, different parameters if you're doing encryption or whatever the case may be. Okay, so thinking about a programmable computational storage drive. So any function is possible, just like our fixed purpose. The difference is we're going to write that function using our favorite programming language instead of implementing it in hardware, which one could argue is also a programming language, but a little bit different. So it can be downloaded dynamically as needs change or arise, and it can be changed dynamically. If you're running a function and you realize that it's not returning the results that you expected, then make a modification to it and download it again and restart. So architecturally, how does that change the block diagram? Well, it's very similar, except that the difference is we've added some kind of applications processor in the light blue box. And it may or may not be the same as your front-end processor. You just have more cores. So generally adding more cores is kind of an easy task. There's not a, it's not a significant effort. Those cores do need to be optimized to run Linux and containers, and I'll get into that in a little bit more detail. And you kind of make it an architectural trade-off as to how many and what performance you want those cores to be based upon a number of factors. Certainly what workloads you want to be able to handle on the drive, how much power you have available in your socket, whatever all the key parameters are that you need to evaluate. You have flexibility in picking the right applications processor or right quantity for the device you're designing. So the main thing that we've changed is we've added a processor or multiple processors and provided a pathway for them to be accessed. All right, so going back to an SSD without computational storage, let's take a look at kind of the flow of data through the controller. So the green shows the pathway of a request arriving from the host, comes in over the host interface and heads over to the DDR. It's probably some kind of a simple descriptor or the beginning of a descriptor that indicates what is the data we want to read and the address for it, and then where do we want to put that data into host memory when we send it back. Your front-end processor is going to analyze that request and is going to build up a transfer descriptor through your controller and send that transfer descriptor over to the flash channel. Flash channel then says, is going to go off and crank away and go get that data, whatever that data is that we're trying to fetch. Much time passes, of course. Flash is kind of inherently slow. So when the flash channel has that data, we have it returning and passing through our data path over to the DDR. This is, of course, the DDR on your device, not in your server. The data in the DDR is extracted and encapsulated in Fabric protocol and then DMA'd to host memory. And then a completion is sent to the host from the front-end processor to say, I've finished your request, host computer. And so for the 16 or 32 terabytes of data, these same 6 steps have to repeat it over and over and over again to move all that data. And clearly that's a lot of power, a lot of time, a lot of cycle spent that could be doing something else. So let's take a look at a computational storage drive data flow. Same kind of request, but a little bit different operation. So this time, the compute arrives from the host and it's going to go to our applications processor. The applications processor notifies the front-end processor to build descriptors. So yes, it does have to know what the structure of the data is on the drive. It has to know that there's a file system down there and that kind of thing, and where to go find that data. And so it sends that request to the appropriate flash channel. The same read data then returns and goes through the data path and into the DDR of the controller. And from there, instead of being packaged in Fabric protocol, it's just pulled out as raw data by the applications processor and compute is performed on it. Now you repeat those steps 2 through 5 in my little list over and over again for that data, and we don't have to move all of that 16 or 32 terabytes over to the host. And when we're done, we finally return the result. So clearly we can see that there's a reduction in the latency to get the data off of the media. There's a latency reduction in moving it to the host, and clearly a big power savings that can be allocated to putting the compute down near the data. All right, so this actually, ironically, some of this was touched on last night in the BOF, but we'll go into a little bit more detail here. It's always good to repeat things. Maybe I'll remember it. You will too. So what do we have to do when we communicate with the CSD? Well, first thing is we have to discover that it is a CSD, because how do we know it's not an ordinary SSD? So there could be fabric changes that are required. So the twig may make recommendations or requests to make to add some kind of commands, or not. But that's certainly what the twig is working on. But what is needed? We definitely need an identifier to say this is computational storage. We need to know the type. Is it fixed or programmable? What is a subtype? You know, let's say it is fixed and you want, and you've got a compression engine. You need to be able to report that that's what it is. The state being, ready or available or offline. And then, of course, some kind of a configuration descriptor so you can configure that and know what are all the valid options that can be configured. So that moves into the second item, of course, the configuration. We have to be able to configure it and make sure that we got it set up the way that we want to use it. So again, there may be some fabric protocol changes. And the twig will make a request or a recommendation. But there are other ways to do it, as we've seen from Stephen. He's got ways to work around that, even in the absence of any fabric changes. But what is needed? We need to have a method to write that configuration data structure so we can program it. We need to have the ability to read and check that what's written, so we know, is what we wrote correct, not correct? Did it accept everything that we thought we programmed, or did something else get accepted instead because we did something that wasn't quite valid? And then, of course, the next is usage. We want to be able to use this. So the usage could be transparent or it could be direct. So transparent is once it's configured, it just happens. We don't have to, there's no further interaction required. Maybe that's compression, for example, where the data just flows in and it's compressed or decompressed. But there's also direct, and so direct seems like a very likely scenario as well. So here there'd be commands from the host that would be required to initiate and retrieve the results. So the example I walked through before was kind of more of an example of a direct, where we set things up and actually had it, you had some kind of a compute operation happen and the results returned. But ultimately, what is needed? We need to have a unified method of interacting, no matter what kind of a computational storage service we're offering or anyone is offering. So Stephen, in the previous talk, he made no bones about his love of NVMe. So certainly NVMe is one likely standard that's going to be used for computational storage drives. NVMe over Fabrics is another very logical one, but there's nothing that says that SAS can't also be used for this. Of course, that requires some discussion and how are we going to make that work, which has not been done. So if you're interested in that, join the twig. But overall, just as Scott had said earlier in his talk this morning, the drive has to operate like normal. It still is to drive at the end of the day. We've got to be able to read data and write data. If there's no data on the drive, we can't do any compute on it. It becomes degenerate. So that has to function just like it is today, whatever it is we do. But then on those compute workloads, we may need some new fabric commands to do the discovery, configuration, and usage, or not. We may not. We may, need driver changes. Almost certainly that, we know for sure that, Stephen and Scott in their two examples, they definitely have some custom drivers that they're using. And obviously, customers aren't going to like having unique drivers for each and every product that's out there. So something unified that we can all agree on is probably going to make it more likely for people to buy it. All right, so switching gears just a little bit here, thinking more in terms of a programmable storage drive and what software would we run on those applications processors that we've added in. Well, how about Linux? I mean, it's open source, it's readily available, it's ubiquitous. I mean, it seems like a great choice. Yeah, you could go off and write a bare metal code to interact with that processor, but why not leverage what is already out there in terms of the Linux ecosystem and open source software? Okay, great, let's run Linux. Well, now what? Well, the next thing would be container software. You know, something like Docker or Kubernetes, so that we can compile on one machine and then download to our drive that's running a different architecture most likely. And then of course our compute function, whatever it is that we want to compute. So let me get into a little bit more detail on each of these. So the Linux, it can be any distribution, including full distributions, like Ubuntu or Debian. But the reality is this is an embedded device, so we're going to want to strip it down and make it small. Yeah, it's an edge server, one could argue. But you know, we don't want to have a lot of wasted space with a very large Linux distribution if we don't need. So why containers? Why do we want to have containers? Well, this allows us, as I had indicated, to write our software on my laptop, which is x86, and then download it to my computational storage drive, which is, well, hopefully ARM. But it could be anything. So it abstracts our underlying OS. You know, you do your development, and you can test it on a different computer. If it is ARM down there, let's say, you can actually test your code on a cloud-based server today and say, is it working the way that I think it is, or the way that I think it should, before you even download it. Overall, it's going to shorten the development time, and it's going to make it real easy to plug in new applications, new compute functions that you want whenever you need to have something different. Just have these containers all ready to go, and you can download different ones as you want to do different tasks on the data. All right, then of course on our application, our compute function, whatever it is that we want to do, that we're going to search for, or do thumbnail generation, or you name whatever the function that you want. It's wide open. Again, with container software, we can compile and test on a machine different from our actual drive, and make sure it works the way that we want it to work and does what we want it to do. All right, so current status. So obviously, a lot of discussion last night at the BOF on computational storage, but there's a lot of work to do. We're very early in the definition, and there was some passionate arguments and discussions going on. So if you're not involved, then I hope you'll consider getting involved. Right now, the TWIG is working on a theory of operations and examples. And I have the task of helping out with one of those, and maybe I'll find some time to work on that soon. All right, but there's a lot of work ahead, particularly interfacing to that compute and downloading those workloads and coming up with a standard that we can all agree on. Like I said, come join us if you aren't already. All right, so I've gone over a lot of information in a hurry. I know everybody's getting anxious for lunch, myself included. The team at ARM has written a computational storage white paper. It's free. You can download it at storage.arm.com, and it goes into a lot more of the benefits of computational storage, migration strategies, and most of all, or best of all, is real-world examples from ARM's partners, some of whom you've already heard from today in this track. And did I mention that it's free? So, all right, with that, thank you. Any questions?
So you mentioned different kinds of computational storage devices, including drives and processors. Now, if you think of a computational storage processor as just an accelerator, at an abstract level at least, it's not a stateful device. Right? You give it, for example, to functions like compression or encryption or fingerprinting, you are giving it some data and it returns some output, but the output does not depend on any previous state. It's just a function. So from that point of view, one could say that's not a storage device. And I'm not saying that because of this we should exclude such devices, but perhaps there's a need for generalizing what NVMe can be used for besides storage. It's not just storage. And maybe this would help in extending the NVMe protocol in some more useful ways.
Well, and so you bring up a really great point, and actually Stephen kind of touched on that in the previous talk as well, in that maybe it would make sense if we had our own protocol, but if we invented it, it would be almost exactly like NVMe at the end of the day. So why not just use NVMe, and maybe it needs a few modifications to support computational storage.
Yeah, no, I wasn't saying that it should be a completely new protocol, but it might require some extensions to NVMe.
Correct.
That might actually help it become even more efficient.
You're absolutely right, and I think that that's one of the topics that the twig has to grapple with, is what are those extensions, and then can we make a request to NVMe, because we are not NVMe at the end of the day. Some of us may be part of NVMe, but they're really two different groups, and so we have to convince the NVMe guys, yeah, this is the direction we should go, and please consider adding this in, and here's why. And so the twig will have to work on that for sure. If there are no other questions, then I'll let everyone go to lunch. All right, thank you.